Hi, good afternoon. I'm Zoltan. I'm happy to see you guys. Today we are going to have a virtual visit. By the way, one technical comment at the very beginning. This is not a formal talk. I'm not going to give you a formal talk. It's rather an informal discussion. So if you have any question, please don't hesitate. Please don't keep it back. Go and ask and cut in at any time. Right, that's Noemi, my side. She's going to go underground. But before doing anything, I think we should start with a bit of an introduction of CERN. So where we are, why we are here, what is the purpose of this this thing. Probably I don't know how much you know about it. So actually, let me just try to reconfigure the thing. Right. That's the bird's eye view of Lake Geneva, the basin of Geneva. Actually, the lake is here. We have the highest mountain
in Europe.
The Mont Blanc. You might see the international airport, and you might see this very nice environment here. You might probably recognize this place. It is written CERN Meran. That's the main campus of CERN. Obviously, that's an acronym. Everybody thinks that the C is a center. Indeed, it's not a center. I have to confess that CERN was rather a council at the very beginning, and the reason was that after the Second World War, we here in Europe we found ourselves by losing the hegemony in the science that we got used to during the previous centuries, and try to find a solution. Actually, this was a very strong problem. This was a very strong dilemma, and therefore 12 countries, together with the UNESCO, started to think about what can be done to regain a little bit of this hegemony, or kind of hegemony. And therefore they produced a council. The council was CERN, Conseil Européen Recherche Nucléaire, and this council gave an advice to create a laboratory somewhere in Europe, where we could install the cutting edge devices, invite the scientists, and probably do something really nice. Therefore, in the 1953, this kind of agreement was made by 12 countries, and we got a green field just outside Geneva. Yeah, that's the nicest place indeed. We got a green field outside Geneva at the border, and that evolved today to the highest lab on this globe. So that's what I was talking about. Actually, by the years, it grew. We had to make another lab called PrefSun, quite close, and we started to organize, started to gain quite a few accelerators. What you might see on this picture, you might see this blue stuff here. Maybe you might recognize the SPS, the superproton synchrotron. This was built somewhere in the beginning of the 80s. This was the first accelerator that made a scientific achievement by proton-proton collision, proton-antiproton collision to be the really exact. And that was the accelerator where the so-called W and Z bosons were discovered. And of course, it made a Nobel Prize. We can think about these bosons later. Actually, they paved the way of the standard model of particles. That is the so far the best working theory on the particle physics. After that, another accelerator was built in order to investigate the properties of the Z boson. That was called Large Electron Positron Collider, and that was a 27-kilometer ring. Actually, today we have another accelerator in this ring, and that was operated between 1989 and 2000. We measured quite a few very precise, well, quite a few parameters with the highest precision of the Z bosons, and we got super sure that that is another particle that is missing from the standard model of particles, and that was the Higgs boson. That was proposed by Professor Higgs and Francois Engler somewhere at the end of the 60s in order to describe why some of the particles have mass, and that had quite a weird theoretical way to operate. But it turned out after the Z boson precision measurements that we do need it. Therefore, the proposal came at the beginning of the 90s to create a much more powerful accelerator that was called Large Hadron Collider. That is indeed, so the past tense is not the best way to describe. That's the Large Hadron Collider, and that's currently operating. Actually, it's going to get the first beam this year, sometime in a week. It has 4 big measurement positions. That's what you might see. It has 4 big measurement positions: the Atlas, the Alice, the LHCb, and CMS. These are 4 big detectors around the LHC ring. Atlas and CMS are general purpose proton collision physics detectors. Are currently sitting at the CMS. Actually, that's not a secret. And there are 2 other detectors, the Alice and the LHCb. The Alice is dedicated for heavy ion collisions, while the LHCb is rather the B quark physics, and therefore the CP violation physics. Indeed, we are going to take a look somewhere around here. This detector is situated, oh yeah, sorry. This detector is situated at the farthest point on this ring, somewhere here, deep inside France, nearby a very nice, very cute village called Sassy. Actually, this is where we are sitting at this moment.
On the surface.
On the surface in the control room. Let's put back my face, and I think I will ask Noemi to walk around here in the control room first, and then we can go down.
Okay.
In the meantime, let me just ask you if you have any questions.
Yeah. Any question?
We have to wait until Noemi turns on her camera, indeed.
If you guys have questions, you just need to come forward because they can't hear us.
Okay. Anyway, what we are going to see today, if we are all lucky, we are going to go underground after the small walking around in this control room, and we will try to get through to the detector itself. Today, the detector is in the commissioning phase. We already turned the magnet on, but we not yet have beams. Therefore, we have a possibility to visit the detector. If everything goes well, and if Noemi can turn on her camera. It's Caterina at this moment, right? Okay, then I let her walk around. Noemi, do you plan to talk a little bit?
Yeah. Okay, I'm on. Okay, so here is the control room, and we have shifters for the detector to. It's kind of babysitting, so make sure that everything works well with the detector and everything is on.
Well, actually, this is a little bit more than a babysitting.
Yeah.
We are in the commissioning phase. We are gradually bringing up all the 120 million data taking channels. We should be sure that everything works, and all the softwares are able to operate together with our hardware. We should be super sure that once we get the first beams, somewhere around the 20th of February, we will be able to take data from the first minute.
Yeah, but I think those are the on-call shifter more than the main shifter here. The central shifters are.
Actually, we have central shifts for this week. What you might see that as we are looking for physics processes that are extremely rare, we always have to be ready to take data. We always have to operate our equipment whenever it is possible. That means that we have. Go ahead.
Sorry, I have a question. You mentioned you had 120 million data points.
Data taking channels, yeah.
What kind of data do you take?
That's a good question. That's a good question. We could start from that side. We are looking for the fundamental interactions of the matter and physics there. Our equipment is looking for physics processes like the Higgs boson creation. We also look for the frontiers of particle physics. We're also looking for non-standard model physics particles. However, what we have to tell about, well, let me just show you one physics that, yep. Okay. What we see in the detector. So that's what the detector looks like when, well, what an event, what a proton-proton collision looks like. During this interaction, we create energy from the collision of the constituents of the proton, and this energy transforms it back into matter. All these transformations are governed by the particle physics, the basic laws of particle physics, and that's what we are measuring. Indeed, let's talk about a particle creation. If we create a Higgs boson, then obviously we want to observe it. And when it goes down. Within this framework, I have to tell you that I have to confess you that these particles that we are creating, W's, Z's, bosons, are extremely short-lived. They live absolutely to the fraction of the second, actually something like 10 to the minus 20, minus 23 seconds. Obviously, these are existing physical objects, but as they decay very fast, we cannot observe them directly. However, what we can observe from them, we can observe their decay particles. That's what we are doing. This detector has to be able to detect the outflying particles' direction, momentum, energy, and also we have to tell what type of particle it is. In order to do that, we have to create quite a complex detector. Some of the detector parts are dedicated for the particle flight direction measurement. Some of them are dedicated for for detecting the particle's energy. And actually, all together, have at this moment 120 million channels that we are going to upgrade during the meantime. You might see how Noemi gets through. What I have to tell that accessing the underground area, we have to have very strong exams, very strong trainings and access rights. There are two reasons why we have to have this. One is that the detector is not without any dangers. Indeed, we are operating at high voltage. We are operating very cold gases. We are operating with high pressure water. Indeed, in this environment, you need to have a safety training. On the other hand, the equipment is quite expensive. Obviously, we want to filter who gets access there. Right. Noemi just arrives to the one of the main elevators we have, and she is going to go underground. Noemi?
Yes, we are just waiting for the elevator to come up. And you will see it's not a small one, it's quite a big. We can accommodate quite a lot of people.
You might see the visitors who came up.
Yeah, I think the capacity is 40 people, but we never put in 40 people. So let's go down. We have, if Caterina, you can show this, we have some levels, of course, minus we are go underground, and the 0 and -1 is the difference between 88 meters, more or less. And this is 97 meters, the -3. I'm thinking -2, show the counting room, and then we go to the detector.
In the meantime, I'm afraid we are going to lose her as the connections the connection in the elevator is quite unstable. But let me show you what is the layout, what we are working in. That's the underground map of the detector zone. You might see this vertical shaft. That's where Noemi is going down. She is going to arrive in this underground service cavern region where we have quite sensitive electronics that are in a close connection with the detector itself. The detector is situated in this detector cavern. Well, you might see that these are quite big caverns. It's 53 meters long, while the other one is something like 84. In order to keep them in keep them intact in this rock, we had to erect a pilier that's something like 7 meters thick. And the byproduct of this guy, that this zone here, the service cavern, happens to be a non-radioactive zone. We can visit at any time even when the beam is on. Right, Noemi. Noemi. I think in the meantime they got frozen. All right, so let me see.
We have a shaft for the crane to crane down equipment, And you could see probably the top of the shaft, the light. That's the roof of the building, the surface building. The light is just for visitors, just to represent that we have to send all the data what we collect with the detector to the surface. And just a sneak peek to -3. So that's really where the feet of the detector, that level is the detector. And you can see that there is a wall, which is a movable wall. Now we are waiting for the beam to come, so therefore this wall is in place. But during the long technical stops, like the year-end one, this wall is moved below us, just in order to
the reason for that
things.
is that if we want to transport things through this vertical shaft, we could move them easily in the detector cavern. Obviously, as Noemi said, that we are preparing for the beam. Now everything is hermetically closed. Noemi?
We go to the counting room. Oh, okay. The door is a bit heavy. This is a bit noisy place, but I hope it doesn't go through the microphone. This is a room for the detector. All these electronics, all equipment, controller, computers, power supply controllers are in this room, in different big cabinets called racks. We can go inside the rack rooms, and we have data taking fibers.
The purpose of this room is that we have quite a few electronics that are closely linked to the detector. If we look at rather the power supplies, Noemi, the power supplies are usually equipments that you cannot put very close to the detector itself. Don't forget that we have a stray magnetic field, also some radiation in the detector cavern. Therefore, these power supplies will not survive the yeah, exactly. These are high voltage power supplies. They would not survive. However, you cannot put them arbitrarily far either from the equipment, because in this case you would get quite a huge loss that should be compensated. Therefore, the compromise is that we put them in this cavern. We are some few tens of meters away from the detector only, and therefore these equipments are on a safe place. Also, there are some other equipments like the computers that are obviously do not tolerate the magnetic field. Also, there are equipments, quite a few, that requires maintenance quite often. And the maintainers, I mean the people, are not very much radiation tolerant, at least by legally. So obviously, many of these devices should be out here. What you might see here, these are the so-called backends. I cannot tell which subdetector they belong to, but definitely are data-taking things. So obviously, they cannot also be taken too far from the detector. Otherwise, you would have a problem with the bandwidth. Right, Noemi, go on.
It's a bit noisy and somebody is drilling, so maybe it's better if you continue. But we continue the walk to the detector cavern. Probably it's better.
Right. So as I have the map in front of me, let me show you where they are. So they are just moving inside in this this underground cavern, and they are going to get to the chicane and get through to the detector one. There will be a technical issue beforehand. Now they are running the camera from a gimbal, and this gimbal will need to be replaced with a simple selfie stick. Otherwise, they wouldn't tolerate the magnetic field. Well, what you might see here is the fourth floor below these racks, what you have just seen. Obviously, for 120 million data channels, we have to have quite a lengthy cabling system. Indeed, just simply don't forget, each of these data taking channels will surely require some power supply, powering. They also need to somehow send out the data, but some of them are also require high voltage, especially the ionization chambers. Some of them require cooling. You might see therefore the cooling pipes. Even from the cooling, we not only use water, but we also have liquid carbon dioxide cooling. We also have C6F14 cooling. And what you not see here, the extra infrastructure, is the superconducting cooling of the magnet that uses a liquid helium. But probably we will see in the next half an hour. Noemi?
Yes, so this is the one of the shaft. That is a kind of shaft which goes down below this pilier.
Yeah, obviously we cannot go straight line with the cables between the detector and this cavern. And the reason for that is the radiation. Obviously, the radiation goes in straight line. Therefore, if you want to trick, if you want not to get the radiation out while the cable goes in, you have to go in a zigzag way. That's why you might see on this map, the connections are always in a kind of a zigzag direction. What you don't see on this picture, however, these vertical shaft that connects for the cabling between the detector and the service cavern.
Yeah.
I'm a little bit surprised that Noemi is silent today.
I'm on or not?
Yes.
Ah,
Yes, you
okay.
are.
Yeah, we just approaching the other access door.
What we have to tell if we are at these doors, you have seen on the surface a green door. Now you see a yellow. Probably for a blink of an eye, you saw a red one. The colors really do have a meaning. The red and the yellow are so-called interlock doors. If we have beam in the machine, these doors are locked. However, as you might realize on this picture, that obviously you can break through this door. However, if you would do so during the beam, shut down the complete 27 kilometers ring. That's a safety thing of the operation of this equipment. We cannot tolerate. We do not want to tolerate the ones together with the beam on.
Yeah, so this door is a bit tricky. It makes sure that only one person goes in, and Caterina has to take the phone. I hope it will be successful for her to go in. No, she has to go again because it has some light gates which checks how many times it is cut, the light, and if it looks like that she's with somebody else, then it doesn't allow her to go in. Okay, now the door closed.
Yeah, in the meantime, we lost them. But in the meantime, until they get back, let me just pop up the detector sketch. I already mentioned you that the detector builds up like an onion. Deep inside the detector, we have the so-called trackers. These are silicon trackers. These are silicon devices. Some of them in the very, very innermost part, they are really like pixel devices. You can think of them like the camera on your mobile phone. Actually, we have something like on this picture, we have 66 million. In reality, now they are more than 80 million after the first upgrade. That's not a big number indeed, I have to tell you. Even in my phone, I have a 100 million pixel camera. The difference, however, that these pixels inside the pixel detector are situated on a I think it is a 4-layer cylinder, therefore making a 3-dimensional camera. And the other thing is, while my phone is able to make something like 8 maximum 10 pictures in a burst mode per second, this camera is able to make 40 million per second. However, as I told you, the operation is exactly the same. These are semiconductor devices, and when the charged particle passes through, the charged particle leaves a small charge at the various levels of this detector. The external part of this, so more the other 6 layers, are strip devices, but they are also silicon devices. The operation is exactly the same. Outside the tracker, so we have the calorimeters. At CMS, we have 2 different types of calorimeters. One is the so-called electromagnetic calorimeter. This is sensitive for electrons and photons. It consists of I think 77,000 of lead tungstenate monocrystals. The work of these crystals is that when a particle just enters in the crystal, the particle just makes the basic physical interactions, something like the pair production, Compton scattering, or ionization. All of them creates low energy photons. And if we collect these photons, we can gather information about the particle's energy, the incident energy. The design of these detectors is such that the particle is completely absorbed inside. Full energy is transformed into photons. There are some other particles containing quarks, hadrons. They cannot be stopped in the crystal calorimeter, therefore we had to build up another detector. That's called, obviously, hadron calorimeter. Instead of the crystals, here we use brass. However, since the brass is not transparent, we had to solve somehow to bring the light out, and therefore we sliced it up, and in the slices we installed scintillators, and taking sample with these scintillators from the avalanche that these particles created, we can also have the energy measurement. But you might see on this picture, indeed, that almost all particles are stopped inside the calorimeters. That's the reason why we designed calorimeters to this size. We want to stop the particles. There are two types of particles that cannot be stopped with these detector components. One is the neutrino that flies through our detector, doesn't leave any trace there, as the neutrino is only a weakly interacting particle. And the other one is the so-called muon. That's the heavier cousin of the electrons. This can also pass through the detector, but as being charged, it can make ionizations on the external part of the detector. These are called, obviously, muon chambers. Muon detection is extremely clean. This detector, obviously, we are not poisoned with any other particles in this. In between the calorimeters and the muon system, you might see the superconducting magnet that creates quite a strong magnetic field. In our detector, it is 3.8 Tesla. That's something like 100,000 times stronger than that of the Earth's magnetic field. Within this this magnetic field, all the charged particle path gets curved. Measuring the sagitta of this curved path can reveal information on the particle momentum. Therefore, you might imagine that all the four things, the direction, the momentum, the energy, and the particle ID, can be measured with this configuration. So you might imagine that everything that is photon doesn't leave trace in the silicon tracker, but leaves a signal in the electromagnetic calorimeter. On contrary, the electron gives a trace in the silicon tracker. It has a curved path. We can measure not only the energy it left, but also the charge of the particle. Same is true for the hadrons. Charged pion, for example, can leave or leaves trace in the silicon tracker, and of course as well signal in the hadron calorimeter, while a neutral hadron particle, neutral hadronic particle, obviously doesn't give any trace in the silicon tracker, but gives a signal in the calorimeter. Muons leave trace in the silicon tracker as being charged. Obviously, no trace in the hadron calorimeter, but signal in the muon system, where we can measure their momentum at the second place. So you might see that this is something like a snaking path. Obviously, inside the magnet, you have one direction of the field that is opposite outside. Noemi?
Hi, so we are already in the detector cover. I don't know if you've seen how we went in, because also we lost a bit of the connection, but I hope now it's stable. What we see, we are in the top of the blockhouse, so basically end of the cavern. If Caterina could show it, and you could ask where the LHC is. Where is the tunnel? The tunnel is below this floor. It's really below us, the LHC, and it continues this way. And the beam pipe is somewhere below this. If you could continue with the picture, behind this orange stuff, because this is the shielding, and it goes the beam pipe somewhere in the middle of the detector, and the collision happens really in the middle. Not just in height, but also in depth as well. And yeah, the goal is to happen really in the center. We plan to walk around a bit to show how it looks like also from different angles. But if you are here, I would like to show also the big shaft. We try to show it with Caterina. It's not easy. So this is the big shaft of the CMS underground. You saw it probably in the drawing, and I don't know if you, Zoltan, mentioned that historically the CMS built in the surface. And
I not yet mentioned. I was about to mention it. However, I was muted.
Okay.
The reason for doing this was not only because we are so clever and we could do this, but rather the reason that building a detector takes an enormous long time, but so does the civil engineering of this huge cavern. If we would have done them one after the other, obviously it would have taken too much time. Therefore, what we decided to build up the detector on the surface. Fortunately, not in one big block, and then we grained it down underground. As you not yet saw, but this detector is is composed of quite a few large sections. We don't need to move it as a one whole, but we could slice it up to 5 borough regions and 3+3 end cap regions, therefore producing 11 plus indeed another 2 big sections of the detector that could be moved separately. The craning was just one reason for this. The other is that all the cables from the detector parts come through at the interfaces of the slices. So what we had to do is just to crane down the individual parts of the detector. The central part that we call ring 0 held the magnet itself. That time none of the internal parts were installed, but even that was far the heaviest part of the detector. That was something like 2,200 tons. You might see on this picture that the total weight is, well, indeed, it's over 14,000 tons. That's quite a large thing. As I already mentioned, that in order to bend the path of the particles, we use magnetic field. This magnetic field must be strong. It's 3.8 Tesla in our case. In order to build it, we had to use a superconductive technology. We use niobium titanium coils, and they are cooled with liquid helium. Yes, that that box is the helium box of the detector. That's even currently filled with 5 cubic meters of helium.
This is why we don't go further.
Exactly, that poses some safety questions. And above that box, you saw the current leads. The current in this detector, in this coil, is something like 18,600 amps. So you might imagine that we need some beefy stuff. If we are at this superconductive magnet, I have to confess that this is the biggest that has ever been built, not by its strength. Obviously, there are much stronger magnets, but it's rather its strength and the size. The inner bore size of the magnet is something like 6 meters. Noemi?
Yeah, so this is quite the top level. You can see the slices. So all this green. So this is one unit. This is the next unit. So these are the end caps, and you were able to see the boroughs. And here, probably this is a better view to see the shaft. This goes also to the surface. So it's 97 meter, something, or 90 meter at least. And now it's closed. So there is a concrete, quite a big concrete block, which is sealing the top of the shaft at this moment. You mentioned the magnet, we plan to go really down there and just show the effect of the magnet as well. Okay. In the meantime, you can talk about the detectors, Zoltan.
Okay.
Or if somebody has questions.
Exactly, this was in my mind that asked for questions.
I have a question. Because I imagine there's quite a lot of radiation produced when you are colliding particles. How do you make sure that it doesn't interfere with the equipment that is measuring and the cables that contain the information as well?
That's a very good question indeed. That's one of the dilemmas, or one of the tasks actually I'm dealing with today even. The radiation obviously depends on where you are in this detector. The point where Noemi and Caterina are at this moment, but they would be during collision. At this moment, there is no collision, as I mentioned. that would not be a very strong. However, inside the detector, really in the center, this radiation might be orders of magnitude bigger. The thing what you brought up, that we have to select material that can withstand the magnetic the radiation field, is absolutely true. During the selection of the components, especially the cables, especially the those parts that are close to the beam, we have to be very prudent. However, if you see these red slabs, the iron slabs of the detector, I also have to tell you that due to the radiation induced by the particle collisions, we might activate up the material at any level. Obviously, it depends also where the material is with respect to the collision point. As you know, the iron slabs usually contain a bit of cobalt and manganese. Both are part of the both are required materials during the iron production. What we try to do here, as the cobalt can activate it up, we try to buy iron that is depleted in cobalt. At least the cobalt content is reduced. However, the manganese content cannot be reused, otherwise the physical properties of the iron slabs would not be sufficient. That's something that we have to live together. What concerns the radiation, we have radiation detectors quite abundant in the detector cavern, and we also have by time to time, when we access, we remove the samples and we measure them, so we can completely follow what is happening inside the detector material. But thanks for the question. This is one of the biggest questions. Next question. If not, then I give back to Noemi once they are back. I'm afraid
Yes.
they. Yeah.
I have one question.
You don't. Okay.
Are there any health risks associated to working in CERN, especially in the detector part?
We have to solve it such a way that not to pose any health risks. In order to achieve that, we control the area. We have, as I told you, radiation detectors, and we have this is one of them. And we also have quite and quite stringent rules as well that we have to keep. Obviously, we cannot get more radiation than you can get, guys. The difference is that we all have our dosimeters, and obviously we are always controlled. I don't know if the answer was correct enough. Noemi?
Yes. So, do you hear me?
Yes,
I'm in
definitely. Yeah.
Okay. So then I ask Caterina to hold the phone. We are at the feet of the detector, and we wrote down some stuff.
Field indicators, indeed.
Field indicators, because you cannot see the magnetic field. You cannot feel with your senses.
So far, the pictures that we are broadcasting looked quite normal, in the sense that it looks like a quite crowded industrial environment, but yes.
And let's get close. I have a bigger one.
As we mentioned, our magnet is already up and running. Inside the magnet, we have something like 3.8 Tesla magnetic field, and it is encapsulated by these red slabs quite efficiently. But indeed, there is some stray field that escapes from the magnet, and that's what Noemi sees. This is
really low.
some tens of
Really...
millitesla we are talking about, maybe 100. Maybe at that point where these wrenches are stacked, it's a couple of hundreds of millitesla, but it is very far from the peak magnetic field. Yep.
Let's try to get.
So it makes something really.
I try to detangle them because they are attaching to each other.
Yeah.
These are just normal chain, just to.
Yeah. So what Noemi.
And you can make quite nice.
Yeah. What Noemi now experiences is quite many times more than that of the Earth magnetic field, quite many times more than the legal limit of the magnetic field exposure, but several magnitudes lower, however, than the real biological effects would start.
Wow.
I just would like to remind that the medical MRI machines operate somewhere around 3 Tesla, and the patients are in the 3 Tesla field. Here, Noemi and Caterina cannot reach the 3 Tesla field as it is encapsulated in the detector. The biological effects are not expected below 10 Tesla. Again, several orders of magnitude more than what they experience now. However, it's quite funny.
Yes. But you, yeah. And of course, the field is different. You can really feel that it wants to attach to the edge where the field is higher, much higher.
As you learned from physics, the magnetic field is stronger around the edges. Obviously, this is what you see here as well.
Have you considered making modern art in the reactor with such a field?
I have to tell you that whenever our guides get in, we end up with some modern arts. Actually, these situations when we can conduct a virtual visit inside the detector cavern when the magnet is on but there is no beam, these are quite rare. We could do this week and probably the beginning of next week, but then we will get the first beams that obviously forbids the human access in the cavern.
Okay.
But if we are here, there is something nice to show. You see this orange stuff? That is kind of an air pad. This allows us to be able to move these big heavy elements. Of course, not me, but the heavy lifting team.
So you might imagine that these elements are very easily more than 1,000 tons. If we want to access the internal part of the detector, they have to be moved away from the way. In order to do that, technically, the only feasible way is to put them on an air pad and tow them away. That's what Noemi shows.
Yes, and what I also want to show is this guy, the
towing machine.
wires. Yeah, with the wires. So it's quite small machine with respect to the
winching machine. Yep.
Yeah. And of course, it operated by an expert team who can do this. It's not a very easy job because you have attachment only in the bottom, the 2 bottom part, and you have to pull it in parallel in sync. So, but it's possible to do it, and this is why the floor is also with some kind of iron slabs to make it really, really flat. Yes. Question, or you want to?
In the
also
meantime,
show-
I think, Noemi, you probably would better to come up and answer the
Okay.
questions from here in the control room.
Yeah.
Unless there is
But
anything else that the audience would like to see in the cover.
We also like to play with the field, so.
Yeah, I think we lost Caterina completely.
Okay, then if you think it's enough from the detector cover, we can go up.
I think it would be better if you would come up, and then
Okay.
yeah, exactly. Oh yeah, Noemi, we got a message from Tristan. They would like to stop the elevator for 30 minutes. Therefore, it is better if you would come up now.
Okay, then we go up now.
Okay.
They will stop the elevator.
Indeed, we have a little bit of a peculiarity concerning the elevator. Probably you already heard about that in a tall buildings. If you get a avaria, let's say a fire, you have to use the stairs instead of the elevator. In our case, it is completely the opposite. If we get any problem on the ground, it's better to use the elevator. Of course, our elevator is constructed such that normally it has its own diesel generator. It is completely independent of the power schema of the rest of the experiment. Obviously, if there is no maintenance, that is foreseen now. And of course, if anything nasty happens, you just need to reach the elevator. It's better not to use the stairs. To confess, our stairs are quite confined and they are also quite steep. So what I can imagine that if you are not trained enough, then you would very probably get a heart attack on the way up. So it is totally contraindicated to use the stairs. For some reason, we lost time. Yep, go ahead.
Does the lift have radiation shielding in it? Is that why
the lift, as I mentioned you, the elevator is running in this shaft well behind this pilier that acts like a radiation shield. So obviously, this zone is not considered as radioactive at all. Somehow Noemi tries to bring the camera out. Noemi, I would propose to come out first.
Yeah,
take
we
the
do
elevator,
it.
and then you do the camera change.
No, it's fine. It's okay.
You already
It's already
did.
done.
Fine. Okay, fine.
Yeah. This was the reason for the bad picture. Sorry for that. Okay, going out is much easier on these access devices.
Obviously, no iris scanning is needed.
Yeah. Okay. Then we go up. Yeah, we will see. I keep the. Okay, we lost them.
Oh, you are still connected, Noemi. Go ahead.
Okay, so it's so we go in the same way. It's the service cavern with all the stuff, and so the good thing with the service cavern is that we can access it basically anytime. So it doesn't depend on the operation
not just
of the
me,
other.
but as you saw, visitors can come in. We have something like 30,000 visitors per year.
Okay, elevator is at -3. Okay, I called it. Okay, it's working.
Don't get scared. This is a maintenance what they would like to do on this.
Sure.
Wait, I have a question. How fast does the elevator travel? Like per
Just count the time.
We start now.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18.
I have to tell you, I started a stopwatch something like 4 seconds after the elevator started. Now we are at about 40 seconds.
And we arrived.
Yeah, I measured 44 seconds. I would say that something like 50 seconds it takes to come up from 88 meters. How you do the math?
2 meters per second. And it's like up.
That's wild.
Doesn't it cause like high levels of like G on a person? How do you manage?
You mean the pressure difference, the pressure changing?
Yeah.
Yes. Okay, I think let's continue with the questions.
Can I ask how much water does the whole site use? Or just
Sorry, I didn't understand the question. How much?
how much? Oh, sorry. How much water does the detector use?
For cooling, you mean?
Yeah.
That's very hard to tell. That's very hard to tell. At least I don't know the exact answer, but that's several hundreds of cubic meters of water for the cooling. Yep, Noemi?
You want to move forward?
Yeah. Let's just switch the camera. Right. Okay.
You can bring your if you guys have questions.
Yep. Hello.
Right.
Hello. I imagine quite a lot of data is collected. You said that the camera takes so many pictures every second. Where is it stored?
That's a very good question. Indeed, I wouldn't call it just a simple camera. It's obviously we can show the events as pictures, but we never think about them as pictures. We rather think about them as data. Indeed, the answer will be quite long, and I apologize for that. So if you would read out all these 120 million channels 40 million times per second, you would get, even on the 8-bit, you would get something like a terabit per second bandwidth requirement, which today is not too far from reality, but when the detector was designed many years ago, it was absolutely a nonsense. What we had to do is to somehow to reduce this data in order to be able to pump out first from the detector and then to store it. Fortunately, we are the elevator stuff. Fortunately, we are quite lucky what concerns physics, as the physics processes that we are looking for are extremely rare. Just to tell you that we talked about the Higgs I have one number running around in my head. That was the probability of the Higgs creation with the configuration we had somewhere around when the Higgs was discovered, somewhere around in 2010, 2012. And statistically, we expected one Higgs creation in every 3,000 billion proton-proton collisions. Also, this is true for other processes we are interested. What we obviously want to see is when the collision of the two partons of the proton creates energy, and this energy decays into particles. This is what we call deeply inelastic scattering. However, most of the overhanging, most of these proton-proton collisions is nothing else but bouncing off the elastic scattering. Fortunately, we are not interested in it. Physics has already collected enough data to test the physics models. What we have to do is to filter out all these elastic scattering and keep only the deeply inelastic ones. That's done by the trigger system. What we can bring up, well, actually, I have to bring this picture back. On this picture, what you might see, you see the detection of the particles. What you can imagine that in a deeply inelastic scattering, for example, among many other possibilities, muons might be created. Muons, if you observe a muons coming from the right point that we can conclude by the detectors in the right time, then you can imagine that this muon was created during the interaction. That's called trigger. We have several other trigger possibilities, but this is probably the easiest to be played.
Yeah, because the proton has no muon inside.
Because the proton has many things inside but the muons.
Yeah.
So if you see a muon coming out at the correct point, coming out at the correct time, then you might imagine that this was a deeply inelastic scattering. And in this case, the detector, well, the muons are quite localized. Only the neighboring detectors will send a signal. That means that if these detectors can discuss with each other, very fast electronics can do that. They can instruct the detector readout system to read out the full 120 million channels. This happens, as I mentioned, we have proton-proton collisions 40 million times per second. This instruction of the detector happens something like 100,000 times per second only. You might imagine we have quite a large factor of data reduction. Once we read out the detector signals, we have a quite sophisticated computer network just above. Well, it's no more above. It's no more above. It's a bit away in the neighboring building. Some thousands of processors we have
in the old control room.
In the old control room as well. And there we have, first of all, quite a lot of time, something like 1 microsecond, to process the data. Of course, this is not a reconstruction. We do not reconstruct the particles themselves, but we can have something about the event topology. And this can also be a subject of a next layer of or next level of the triggering system that can select those topologies that we can simulate to be. This happens something like 1,000 times per second. And these 1,000 events are streamed out to the computer center at CERN in Meran and stored there on the tier 0 level of the worldwide computing grid. I don't know if it was satisfying. Something I wanted to show this. That's a picture I stolen some months ago. This tells about the data sizes of the known sources. So, for example, the Netflix data size is something like in streaming, something like 100,000 petabytes per year. With comparison to that, that's the size of the data of the LHC row. Obviously, this is what we don't read out all, but you might imagine in 2018, this would be something like 10 million times 10 million petabytes. And so that's an amount of data that is unbelievable. If we use the trigger, if we apply the trigger, we get to this 160 petabytes per year, which is still quite a large amount, but something that can technically be handled. Right?
Thank you.
Thank you.
I have a question. So the discovery of Higgs boson has happened over a decade ago, and what are the goals or the objectives that you are trying to measure now? Like, what are the things that you want to discover, like with this current like experiments? Yes.
Obviously, we have a very successful model called the standard model of particles, as I've already mentioned. However, we know that this model is not complete. However, we know that there are some observations that tells that something needs to be adjusted. In order to do that, we try to look for signatures outside of the standard model to allow the theorists to create better models. From another point of view, if I would just show you the menagerie of the standard model particles, as this thingy, that's the particles that we know today in the standard model, and that's, of course, physics we more or less understand. However, I have to confess that these are only 5% of the mass of the universe. There should be something that holds together the galaxies called dark matter that we have no clue what it might be. Definitely, the dark matter particles are not shown in this picture. That's also something that we want to hope that at some point we will understand with these detectors. The third thing is that on this picture, you might see particles, and you might see the particles that create the matter and the particles that are responsible for the particle interactions. They behave completely differently. Why these particles are subject to the Pauli exclusion, these are not. These are called fermions. As the statistics, they obey the Fermi statistics, while the other guys are the bosons for the Bose-Einstein statistics obeying. Don't know why this happens. Don't know if this is a symmetry breaking. Obviously, it is. We don't know how this happens, how this happened in the nature. That's something we want to understand. Another thing is that from the particles that create matter, you might see that we have 3 generations. Only the first one is what we see in nature. The other 2 can be created in particle accelerators, but they are very short-lived. We know that there are only 3 types of neutrinos exist. We have already measured it and we proved. But we don't know how many generations of the quarks exist. We haven't seen anything else but 3 so far. Again, a question. Why 3? Why not more? Why not less? These are the questions, one of the biggest questions that we have. Also, you probably heard about the electroweak unification thing. What we expected from the theory that there should be a situation, an energy density level, where the electromagnetic and the weak interaction cannot be distincted from each other. This we have already reached, and also the standard model nicely describes it. Also, there should be something that we expect for the strong interaction unification, as the GUT, the grand unification theory. That's also something that changes somewhat the physics, and that's clue we would like to see. The unfortunate thing is that the grand unification is something like 12 orders of magnitude away from the energy levels that we are using today. But if the theory is correct, there might be something clue, there might be some ghost things that we should see on this energy levels. I think that's the brief answer to your question.
And I have one more question, which is like quite closely connected to the previous one, which is that I read about the future Circle-I Collider, and it's supposed to be like bigger than the LHC now. And wouldn't it give the physicist like a proper level of like upgrade of magnitude to discover these things?
Let me just bring up this one. So that's the plan for the future. What we are somewhere here on the Large Hadron Collider, and you might see that the plans for the new accelerator is this. We plan to build an accelerator that is something like 90 kilometers long, and that could reach up to something like 100 tera electron volts, something like 7 times more than what we reach today. I'm afraid that this will not get much closer to the grand unification, but at least at this energy level, according to the theorists, we will see the so-called self-coupling of the Higgs boson, which is still something that we need to understand from the standard model, or at least check with respect to the theory, what the theory predictions. Also, there is no guarantee, but very probably we would see something from the dark matter. That's the reason why we would like to build this extremely large accelerator. This would foresee to get operational somewhere around 2070, at the end of your professional life.
It's a very big, ambitious project.
It's a very ambitious project. This will be anyway a two-step project. If we manage to drill this underground tunnel, which anyway, believe or not, the most expensive part of the whole project, the first attempt will be an electron-positron collider, a lepton collider, that will be called FCCEE project, and that will hopefully be able to produce a lot more Higgs bosons that we can do today, and can precisely measure the Higgs parameters. After this project, the tunnel will be emptied, just like what happened to the LHC, and will be populated with the so-called FCC-HH components, where we plan to collide again protons together somewhere around 100 tera electron volts. That will be somewhere around the end of this century.
But the closer future is that we will have a long shutdown for the LHC, and after that the luminosity will be
exactly.
tuned up for
Exactly.
the LHC.
We are going to crank up the luminosity and not the energy. That's going to start this July and will last something like 3 years.
Yes.
The reason why we want to change the luminosity instead of the energy is quite simple. In order to change the energy, we would need to install much stronger dipole magnets inside the ring that we not yet have the technology for. But the physics that we are interested, as I mentioned, is very rare. Therefore, increasing the
number of collisions,
roughly speaking, the number of collisions, we could get more data, we could get more statistics on these very rare events, and that could give a hint if there is something as a shadow or a ghost, as I mentioned, from the physics from higher energies.
This may be a silly question, but how does a larger collider result in new discoveries? Can't you use the current Large Hadron Collider and, like you said, increase the power when the technology becomes available of the magnets to give the particles more energy?
Well, increasing the magnetic field on an industrial way, that means that we use several hundreds, even thousands of magnets, superconducting electromagnets. It is not easy. At this moment, we are using this niobium titanium technology that can go up to something like 10 Tesla. We almost completely use this range with the current accelerator. There are researches and also technological researches to apply new material, for example, the niobium 310 technology that could go up to 15 Tesla. At this moment, that's what we see. Obviously, there are much stronger magnets on in the research sphere, but obviously they are much smaller in scale.
But we would prove it if we could have higher energy collision, because there are different probabilities for different
obviously, as we call cross section, this probability, this scales with the center of mass energy, therefore the beam maximum energy. However, it is not so easy to change on a circular accelerator, as I said. One way is what you see here. If we use the current technology, more or less the current technology, obviously this is going to be cranked up by then. If you increase the radius of the accelerator, you could go up to higher energies with the same magnetic field. Obviously, as you might see, going around Geneva, digging a tunnel below the Lake Geneva, you don't see from this picture, but this is a hill here, Mont Salève, going around in very various geological situations will not be an easy task.
And we have to put it underground because it's a habitated area. So
on the other hand,
the
average
there is a
depth,
city, so
the average depth of this accelerator will be something like 400 meters.
Yes. We will see.
Exactly. Well, you will see. I will be retired by then.
I have one more technical question. So you mentioned that the energy consumption is quite high of the entire CERN. Where do you get the power to do everything?
I have to correct you. I didn't mention that the energy consumption is very high. Instead, I would like to say it is very low. What we consume, if all the accelerators, the full accelerator complex is on, together with my desk lamp, we consume something like 200 megawatts, 180 something. We can call it 200 megawatts. This is obviously not an extreme big consumption. It's something like a small city like Geneva in the neighborhood. Don't laugh at it. This is something like 300,000 people, or we could tell Debrecen as well. Obviously, this energy we have to buy from the local energy providers. Our provider is the French network provider called EDF. We get the electricity from them. But what I would like to tell that 200 megawatts is not an extremely large amount. If I would compare it to the nuclear power plants that are very common around, France's second biggest or third biggest nuclear power plant is not too far from here, that's called Bougie, and that has something like 5,000 megawatts in built power.
So you're eco-friendly.
We try to be. Actually, it is not just the energy consumption. Obviously, we try not to pay too much money on the energy. Therefore, we definitely try not to waste it. But also, the cooling water we try to use. The cooling water that returns from the detector after a heat exchanger, of course, can heat the neighboring houses in the villages. That's something like a new project that we try to implement pretty soon.
That's really cool. So people are showering in the cooling water.
That's why I said that after a heat exchanging. Not the direct water. That's a demineralized water that we use. Not very health friendly.
Thank you so much.
You're welcome. It was our pleasure to be together with you today, and I think at some point we can continue. And I promise that I will prepare a bit better for the next session. All right. Have a nice day. Ciao, ciao.
Ciao, ciao.